In this video, we're going to learn about standard deviation and variance. So here we want to compute the variance sigma squared and the standard deviation sigma of the dataset below. The dataset is 1, 2, 5, 7, 8. Alright, so first of all, what are variance and standard deviation? Well, they're metrics on a dataset, and they measure the dispersion of a dataset. In other words, how spread out the data is. First of all, let's focus on variance. So this is what variance is. Variance, in other words, sigma squared, that's the symbolic notation for it, that's equal to the average squared distance from the mean of the data. Our first step to calculating the variance is to calculate the mean. Let's do that over here. For this dataset, the mean is the sum 1 plus 2 plus 5 plus 7 plus 8 divided by the number of values we summed up. That's 1, 2, 3, 4, 5. So over 5, which is equal to 23 over 5, or 4.6. Okay, so we want to calculate the average squared distance from 4.6. And why don't we write that down here? So sigma squared, the variance, is equal to the average squared distance from the mean. So we have to sum up all of the squared distances from 4.6 and then divide by 5. So why don't we do the sum first? So we're summing up the distance between 1 and 4.6. In the end, we're squaring it, so it doesn't really matter what order we put it in. We can do 1 minus 4.6 or 4.6 minus 1 and square it. Conventionally, we always have it in the format of data value minus the mean, so we'll just do that for the rest of them. So 1 minus 4.6 squared, then plus 2 minus 4.6 squared, and then plus 5 minus 4.6 squared, so on, plus 7 minus 4.6 squared, and then plus 8 minus 4.6 squared. And that's all over the number of terms we're adding up, because we're taking the average. Again, this is 5 terms, so all over 5. Okay, so we just put this into our calculator, we calculate it, and the result for the numerator, we get 37.2, and that's over 5, and that divides to 7.44. So there is our variance, 7.44. Now let's compute the standard deviation. So the standard deviation, that's just sigma. And because we know the variance, which is sigma squared, it's really easy to compute the standard deviation. To get sigma, you just have to take the square root of sigma squared. So we really just have to take the square root of 7.44 squared, because we found that 7.44 was sigma. So we punch this in our calculator, and we get that this is approximately 2.73. So there we go. There is our standard deviation. Alright, so looking back, here are the two key things to remember. The variance, sigma squared, is the average squared distance from the mean. That's the first thing to remember. And the second thing to remember is the standard deviation is just sigma, and that can be calculated as the square root of sigma squared, where sigma squared is the variance. Here's another problem. Here we want to compute the variance, sigma squared, and the standard deviation, sigma, of the dataset below. 1, 3, 3, 4, 5, 6, 9, 10, 11, 11, 11, 12, 13, 13, 13. Oh boy, that's a lot of numbers. And it's going to be really annoying to do the full computation like we did previously, now that we have so many numbers. But thankfully, there's another formula that we can use for variance, and it goes like this. So variance, or sigma squared, can also be computed as the mean of the squared values minus the mean squared. So to be very explicit, the bar here just means take the mean, so mean of, and then the expression under the bar says what we do to the values before we take the mean. So that's saying we square the values before we take the mean. So this is really the mean of 1 squared, 3 squared, 3 squared, 4 squared, and so on, the rest of the values squared. Whereas this here, x bar, the quantity squared, that's just saying take the mean of the values as they are, so 1, 3, 3, 4, so on, and then square the result. Alright, so why don't we do this calculation off to the side? The mean of these squared values, we'll do that first. So we're really just adding up all the squared values. So 1 squared plus 3 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 9 squared plus 10 squared plus 11 squared plus 11 squared plus 11 squared plus 12 squared plus 13 squared plus 13 squared plus 13 squared, and divide that by the total number of values we're adding up. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So divided by 15. We can just punch that into our calculator and we get that's approximately equal to 86.07. Next we'll do the mean of the entries as they are and then square that. That's pretty similar. We just don't have the squares here this time. So just 1 plus 3 plus 3 plus 4 plus 5 plus 6 plus 9 plus 10 plus 11 plus 11 plus 11 plus 12 plus 13 plus 13 plus 13. That's all over 15 because there are still 15 entries, but we're wanting to square that afterwards. And the result for that, if we punch that in the calculator, that's about 69.44. So the variance is then equal to, well, approximately equal to, because we're rounding the results a little bit, 86.07 minus 69.44, which is equal to 16.63. So there we go, that's our variance. Now this result is exactly the same as the result that we'd get if we used the previous variance formula, the one where we explicitly computed the average of the squared distances from the means. This formula here, even though it may not look like it, it also computes the average squared distance from the mean. But we didn't introduce it initially because we wanted to do the intuitive, straightforward way first. But now we can use this less intuitive hack to save time when we have to do variance computations on large data sets. Okay, so that's the variance, and then the standard deviation is still sigma, and that's still very straightforward to compute now that we know the variance sigma squared. So to get sigma, we just take the square root of sigma squared. So the square root of 16.63 squared, punch that into the calculator, and you get that's approximately equal to 4.08. So there's our standard deviation. Great, so now we know how to compute standard deviation and variance, which give us a measure of the dispersion of a dataset. And in the future, when we learn how to plot datasets, we'll get a better idea of what it means visually for a dataset to be dispersed.